It's not a problem.
Well, it's a feature, but it's a bug.
It's
Well,
a
I don't know.
Yeah. Okay, so we talked about this cable that you have. You have this guy. Since we got the back, I'll show you.
Okay.
This cable is designed to plug into here. Okay. Oh, there's your. There. I caught you. So this plugs in there,
Okay.
and
I
obviously you know where that goes, right?
excuse me.
Okay, I can't
I need some space here
So
to
this system will be limited to 40
video
volts,
record it.
the way it is, unless you
Here.
figure out where to plug that in, and I can't tell you how to do that.
right?
'Cause that would be advisable
Yeah,
in a
they are
dangerous
moving,
situation,
you know.
I can't do that. You guys are smart people.
So,
You figure
Yeah, I
that out.
came up with this, so.
Okay. Okay.
Okay, so that's actually a good safety feature. If most of your people are not needing greater than 40 volts, leave it out. And you should probably only certain people should know about that. People that need to go higher than 40 volts. You don't want to enable this to do 200 volts unless you need it, because it's by.
We're not gonna do that a lot, actually.
Okay,
Right.
because there's safety requirements that I'm sure the university would like to know about. And so if you've got 200 volt equipment, it has to have a safety enclosure. And the way that would work, you have an issue because you have two probe stations. The way that would work is they literally put a big giant box around this, and it would have a door. And the door would have a switch on it, and that switch is that, basically, you see. So when the door's open, it opens up the connection on this cable, and it limits the power on the machine. Okay, so that's the way it would. There's a couple ways to do it. They do it a lot with a big enclosure, or sometimes they put 4 posts, and they have lasers that shoot around it. And if your hand breaks the laser, it shuts it off. That's another way. They call it a light safe enclosure. So that's another way to do it. There's a lot of ways to do it, but whenever you have a piece of equipment that drives more than 42 volts, it's considered dangerous, and you have to shield your operators from being able to touch the device. And one thing I want to warn you about is an SMU has very high impedance. It has a very high input impedance. It's 10 to the 14, 10 to 18 is a big number.
So the current will go through our body first.
The current, well, no, what I'm trying to get at is off does not mean off necessarily. Okay, when the SMU is off, people think it's safe. I can go grab my device and unplug it. If your device has capacitance, this is not going to discharge it, right? Because the impedance is so high, you could have a charge on your device for quite a while after you turn off the SMU. So just be aware of that off does not mean off when you talk about SMUs. You know, because somebody will get hit and they'll call us and they'll blame us. No, it's doing what it's supposed to do. The system is off. It's your device that's not off. Your device will have a charge on it still. Most equipment has low enough impedance that when you turn off the equipment, there's still impedance, low enough impedance in the instrument that it will naturally discharge your device, right? This won't do that. Okay, just so you understand that. Because the idea here is that you don't want your circuit to see this box. It needs to be high enough impedance that it doesn't load down your circuit, right? That's the whole idea. It doesn't. You don't want to have this load down your equipment, your device. So that's just got to understand that this is not it's not like using a fluke DMM, right? It has a 10 meg impedance. It's going to discharge anything pretty quickly. This isn't going to. Okay, just so you understand that. So what a lot of people will do if they're doing a lot of high voltage, they'll have a discharge probe that's got some it's got a resistance to ground. So you ground it to a good ground, and you just touch your device with the probe before you contact it with your fingers. Just be aware. You don't want to use a dead short, because then it's a high energy, spike when you hit it. So you need some resistance in that probe. They make special probes for that. We sell them if you're interested. We have them, but you don't want to just use a ground wire. Right?
What are they called?
It's called a discharge probe. It's got a big handle that's insulated. It's got a shield around it, so you can't accidentally get nailed by it. Okay, so.
So one part is the device capacitance, right? But our devices are very small, so the probably don't hold much.
Not
Right,
the
but what
cable,
about
these
the
pieces.
probes and the cables? Yeah.
Yeah, it's
So
all that
amazing.
capacitance
Yeah.
adds up, right? And so the more cabling you got, the more capacitance you got, and all those things will matter, right?
Right.
So that's why we always talk about about cable length. Cable length is a big deal with this, right? We want to keep our cables as short as possible. You guys did it right. Customer we were at yesterday didn't do it right. They had coils of cable, and it's like, and I always tell them, don't order long cables. Long cables are bad, right? They have inductance, they have capacitance. So the deal is, the best performance you're ever going to get out of a piece of equipment is right out of the back of the instrument, right? Anything you attach to it from there, you degrade your capabilities. That's just the way it is. It's every single connector, every adapter, every cable, every inch of cable, you're reducing your capabilities to make good measurements every time you add something to it. So the less things you can add, the better. In fact, I don't like these. I told you about these. Because now you're adding an additional connector. You're adding an additional connector, which gives you opportunities for reflections, for your CV measurements at high frequency. That signal can reflect back from, if you've got a little bit wonky connection, you'll get a reflection back to the source, and you'll get bad results. So I try to avoid these kind of things as much as possible. The best situation is if you can go right from the instrument to your probe and be done with it. That's the best. I mean, these are convenient, but and again, this is if you're making very sensitive measurements, then it's where it matters, or high frequency measurements, it matters. If you're making volts and amps measurements, who cares? You're not going to have to worry about it. But if you're trying to measure femtoamps and attoamps and do CV at 10 megahertz, those things can matter, right? So you want to be aware. And another thing I noticed is it's the cables. You want to take very good care of these cables. And I noticed there was some kinks in one of these cables. You want to be very careful with these, because a kink is another opportunity for a reflection, right? Any kind of damage to these cables will affect your measurements. These are like I said, these are sensitive measurements, so they require you take care of this stuff, right? And make sure you always torque these connections. We provide you with a torque wrench. This is it. Make sure you use this. Okay, these have to be torqued to a specific torque. If they're not, again, reflections. You will get bad measurements. Okay, so some people think they have calibrated fingers and they don't have to worry about it. Don't have to worry about this. But no, you should use this all the time. That's why we provide it. Okay, I noticed these are torqued because I can't get them off. So those are torqued. But this will click when it gets the right torque. So you turn it till you hear it click, and then you stop. Okay. So that's the way that works. Now we took out your CVIV, so I took your preamp out of the CVIV. I put it back here. So we're gonna just come directly off the system now. And these are you got 4 channels. Are you gonna use the 4th channel?
Yeah, we need it.
Okay, then we need a cable for that.
Yeah. We had a cable for it.
We have a cable. It wasn't on here when I got here.
We definitely have more cables than channels.
Okay, we need this.
And those are triaxial
This
cables.
one.
So,
Yeah, does everybody understand triax?
yeah,
Yeah?
I guess.
Don't be shy if you don't, because a lot of people have never seen triax. And do you know why you need triax? Yeah? You need triax for any current measurements that are less than 100 nanoamps. You need to use triax. You're not going to be able to get a low current measurement through coaxial cables. Because the triax has a second guard or a second shield on it.
I guess we're not planning on moving this anytime soon. So we can just keep
Yeah, it should be fixed here, yeah,
Yeah.
because it travel a lot of times, a lot of places.
Right.
Let's keep it there.
Yeah, it should be there.
Well, the question is once, if you want to use either of the probe station, you might have to switch back and forth.
Yeah, you just have to switch
you know.
cables around, that's all.
You know, actually I'm planning for having a moving shelf.
Okay.
These equipments with some power supply sticks so that
A lot
we
of
can.
people put them on a cart.
Yeah, that's what I'm planning actually, some moving
Right.
shelf so
I mean,
that we can move.
Hmm.
Yeah, so
Connecting and disconnecting
Yes.
cables is not a very good thing.
Okay, I'm just gonna get these out of my way here. Does everybody understand what's back here? So while we got it turned around, you got 9 slots with 4 SMUs and a CV meter. There's a ground unit Are you familiar with the ground unit? Ground unit's basically another SMU, but it can't measure. It can only supply 0 volts.
Zero.
So, if you want to, a lot of people to save money, if they need to do 4 terminals, they'll buy 3 SMUs and they use the ground unit for the 4th ground. You almost always have a ground, right, on your device. But the SMU's better at ground than the ground unit is. So since you have 4 SMUs, pretend this doesn't exist. You don't need it. Because your best accuracy is always on the lowest range. The ground unit doesn't have ranges. The SMUs do. So you can set the SMU to a very low voltage range, source 0 volts, and you can have a very good ground. Okay? If you had it on a high voltage range and you source 0 volts, you're not going to have a good ground. So just so you know that. You always want to, your highest accuracy is on your lowest ranges, always, right? And since there's no ranges on this, it's not going to give you a great ground. It's okay, but it's not great. The other thing the SMU does is it allows you to measure on that leg, where the ground unit doesn't. Just sources 0 volts, no measure. So if you ever select ground unit, you'll see under measure it says NA. It won't let you. Okay. So let's spin this guy around. This goes with the
I hope we will have enough space.
I think we do.
And then we can take out the shelf.
Oh, that's right. Okay. That's another thing. The CVIV, it has to be plugged into USB 3 port. Okay, which all the ones on the rear are USB 3, but there's USB 2s on the front. So it needs more power than USB 2 can provide. So you got to make sure you're using USB 3. This should go with that CVIV.
Yeah, the serious switch one, yes.
No.
Are we going to be using those, the red ones?
Are we going to be doing any TV measurements today? We will.
We should, yeah.
We should.
Um,
I thought they just go straight.
So what's our goal are we doing some training for some new people? What's the
Yeah,
goal?
last time all of them was not there, so there are some new people here
Okay.
who will be working with these machines.
Did you get a little fixture with this? A little box
With the transistor, you remember?
with the transistors? Did you get one
Yes,
of those?
yes.
Because from a training standpoint, that's the best way to go here. I don't have to use your probe station then. It's just a little easier to understand. So I'd rather do that. But okay, so one thing here is we've made some hardware changes here. We've gotten rid of the CVIV. We've reconnected your preamp. So we've made hardware changes. So whenever you make hardware changes on this machine, you've got to run KCON.
Isn't this Windows 10?
This is Windows 7.
Is it Windows?
And that's why. See, it detected that we made a change. It says there's a configuration error. So it's not seeing what it expected to see. It's expecting to see the CVIV. It's not there. So Clarius crashed. It didn't crash. It just said, I'm done. I can't work. So what you got to do is you got to run KCON.
Yeah. We were playing there, but it didn't give us a lot of options to do it.
Okay. So KCON shows you all your hardware over here. It's showing the CVIV because that's what it had last time it was on. So that's got to go away. So to make this correct, you got to do an update and say, okay, make sure you're not connected to any devices when you do that. And you let this run. And what you'll see is this will go away. There, it's gone. And the little caret here on SMU1, that's your preamp. Okay, so if I open that, there's my preamp. So all my hardware has to be recognized by the machine. It will only allow you to use hardware that's recognized. If it's not recognized, Clarius won't recognize it either. Okay, so this, you have to save this. This will, there we go. This will create a configuration file that Clarius will use to determine which hardware is available to it. Okay, so there's another. This is how, and here's how we've determined that the CVIV was bad. Every one of this piece of hardware in here there's a there's a self-test. It's not showing it for some reason. Why is it not showing the self-test? Very strange. Oh, there it is. There it is. So this is to test the hardware. So for any piece of hardware that's in the machine, if you have a question on it, you can go here and run the self-test. We ran the self-test on the CVIV and it failed miserably. So it's clearly got a problem. It looked like a calibration error, but it was so far off. It's not calibration. It's something went south on it. So that's KCON. Once you got this set up, you can then go back to Clarius, and then Clarius should load up without any beeps or warnings or errors. Okay. Now this. Are there any transistors in here? No. Where's the transistor?
Yeah.
Oh, there they are.
Yeah.
Okay. Okay, so we have this default project, which is a good place to start. So what I'm going to do is I'm going to grab one of these guys. This is also a good way to verify the operation of the system, because these tests all work. If you can run one transistor test that tests all the hardware, you can use everything, run one sweep. But make sure, if you use these transistors, look at them carefully, because out of the box I got a shorting wire around them, and you got to pull that off, or obviously it's not going to work. And what I'm going to do is I'm going to plug this guy in there. And you'll notice there's two sides of the fixture. This side's capped, because this is for AC measurements, and you don't have a pulse card in here, so we're not going to use that. But we can use it for CV. We can do the CV measurements across that. Or we can do them on this side. It's not going to really matter.
And does it have the specific name of the lakes? Which one is the drain, gate, and source?
Yes, it's all marked on there.
Marked there,
Yeah.
okay.
And it even tells you which SMU, and those correspond to the default project.
Okay.
Okay? So here's what, we have the mouse here, right? Yeah. Here's what we're going to do. Since we're not using the CVIV, we don't care about this anymore. So I'm going to do a family of curves test. So what we would expect is a typical family of curves sweep, where we're gonna step our gate. That's our four sweeps, and we're gonna sweep the drain to source. So all your SMUs they're in lock sync together. They're all going to trigger at the same time, within nanoseconds of each other. They don't even have to be doing the same thing. So what we're going to do is we're going to use one SMU to do a step function on the gate. We're going to use another SMU to do a sweep function. So for every step, we're going to do a complete sweep, right? And they're going to trigger at the same time. So what I'm going to... Do I have to go over Clarius at all? Does everybody kind of understand the
We have a
Clarius?
general idea, but if you go like very fast, I think you might teach
Okay.
us some stuff.
So
we
it's a
don't know.
three-step process: select, configure, and analyze. Right. So it's pretty simple to understand. I mean, most of the time I can walk away, you'll figure it out. It's pretty easy. So first, you're going to select the kind of test you want to perform on what type of device. Then you're going to configure that test, and then you're going to analyze the data. That's the way it typically works. So by default, it shows you everything. You can filter this down by using some of these things over here. You can filter down so it only show you a smaller group of what you want. Now there's tests, there's devices, which are all the different types of devices that we can test. These are all built into the system. They're already done for you. There's actions. An action can be like beep the beep, or display a dialog box, maybe tell somebody to move a connection or something. To control the CVIV, which doesn't work. Switching, if you've got a cryo chamber with a Lakeshore controller, it can control that directly from here.
So now without configuring it, it'll automatically use SMU1 when you connect that, right? Because using the switch, we had to select SMU and tell it what it's.
Right, because you had a choice between SMU or CV.
Yeah.
Now you're not gonna have a choice. If you select SMU, it's going to drive the SMU lines. If you select CV, it's going to drive the CV lines. So you have to have whichever connected. You have to have whichever one connected that you want to use at the time.
Okay.
Okay. So we're going to use SMUs at first here, but you've got a typical Windows-style project layout, and the way it works is you start by creating a project, and we call this one default. So each of you can have your own projects, right? And within your project, you can have devices. So here we got a 4-terminal FET, a 3-terminal FET, 2-wire resistor. It doesn't even have to be the same device. You can have all different kind of devices. And then within the device, you can have your tests. So what you can do is I can go up to, say, this top level where the 4-terminal FET, and if I run that, it will run every test under there that's checked, one after another. Boom, 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 right down the line. If I go to just the test, the individual test, and I hit run, it's only going to run that test, you see? So what we can do is we can sequence tests. We can
You don't have to uncheck all the others.
not if I want to run an individual test. I just select that test and I
Okay.
run it. But for instance, if I want to control some other piece of equipment, say a cryo chamber or an oscilloscope or whatever, a heated chuck, whatever, I can write a test that I can insert in here, and I can have them both checked, and I can run them both sequentially, right? So I can have a characterization. I can set a temperature, characterization, set a temperature, characterization, and I can run them all sequentially, right? And in the test for the temperature chamber, you can even have soak times built into it. So you can hit run and walk away for the weekend, and then when you come back, you'll have all your data. Okay? So the box has a built-in GPIB controller. It's not a GPIB instrument per se. It's a controller. Because it's got a PC, it's your master, it's your talker by default. And so that means any GPIB instruments you have that you want to control with this, you can. There's a whole bunch of examples already done for you of different instruments in there. GPIB is pretty straightforward. It's a bunch of reads and writes. So if you've got an example that talks to one instrument, you can talk to any instrument just by changing the commands that you're reading and writing, right? So pretty simple. So, but like I said, it defaults as a controller. If you want to, you can use this just like any other dumb instrument where you control it through LabVIEW, MATLAB from a laptop or another computer.
Yeah,
And to
iPhone is
do
better
that,
than
you
DSLR.
would have to turn around the GPIB bus. And to do that, that's what this KIXI is. KIXI,
It's
when you
maybe
run
because
KIXI,
it's
it
bit
converts
tiny.
the GPIB to be a
use it.
listener instead of a talker. So now it's just
How big
another dumb instrument,
is
and it's
another
waiting
bit?
for you to send it a
It's
command.
a small
Okay,
scale.
so you'll get like a command line style interface, and when you send commands through your MATLAB or your LabVIEW, which can be on this machine, by the way, since it's a PC, then it will respond to those commands, and it'll act just like any other instrument would. Okay, so that's how you reverse the talker-listener roles of the machine. I don't know why you do that, but because you lose a lot of the nice features of Clarius when you do that, because now it's just a command line style display, and it only allows you to throw one graph up, and that's it. That's all you can do. And you don't have a pulsar, but if you have a pulsar, you can't use it anyway because the speed of the pulsar is faster than the communication. So that it creates a little bit of a problem. So that kind of tells you what you got here. Okay. It's set up to do wafer maps as well. If you've got a wafer with a bunch of sites, you can map all the sites, pass, fail, things like that. That's kind of cool. It can even control an automated probe station, so indexing and probe up, down, chuck up, down, all that. It can control all that stuff for you. And then you've got projects. These are built-in projects for specific technologies, right? For MOS technologies, kit capacitor measurements, charge pumping, trapping, all those types of things. So you can. So this is a project that we've loaded. Question? No? Okay.
But you can also set up completely your own test, right? Your own IV.
Yes.
Because I don't know about this one, but when I used the previous version of a different one,
Yes.
the built-in ones were always kind of clunky for our transistors, so I just did my own and
That's
whatever
correct.
I wanted, right?
So that brings me to the next point. There's two different types of tests that are in this machine. There's ITMs and UTMs, is what we call them. An ITM is an interactive test module. That's what most of these tests are. They're interactive in that we created the GUI, we've put the pull-ups and the pull-downs, and we've decided the limits and the default values. So we've kind of decided what you need, and we've given you that. So it's limited to what we've given you. You can't go outside of that. Where a UTM you create a custom test, and that's where the compiler comes in, where you build a test using C, C++, and you create the GUI. You put the controls on the GUI. You decide the defaults. You decide the limits. You do it all.
Can I sort of do something in between where, I don't
can
want to
mix and
write
match
C, but I just want to say, I have 3 SMUs, this one set it to 0 volts, this
Yes.
one, sweep current this way, this one, this
Yes,
limit.
there's a generic device.
generic test, yeah, yeah.
There's
so-
a
so-
generic device that looks just like a box with wires coming out of it.
Exactly.
And then you can wire up what you want. So that's the other point here, is that if I go to a test, see, this shows a device here, that means
Right.
nothing.
Right.
What
It's just a
matters is
symbol,
what
right?
you
Yeah.
do.
Exactly.
What you do on each pin is what matters. This is just a bitmap. I could put a picture of my kids on there. It doesn't really matter. It's just a bitmap file, right? So this is what matters, not this.
Mm.
Okay? So I could test a resistor off of this if I want. It really doesn't matter. It's what you do on each pin that matters. Okay? So yeah, like you said, so the generic one just puts a blank box there, so you don't know what it is really, but it has four leads, and you can tie whatever
Right.
you want to whatever lead and do whatever you want,
Mm.
right? So, but these are all pre-done for you by us, you know, for the typical things you do. But they're limited in their functionality because you can only do what we've given
Right.
you, right? So if you need to go outside of that, that's where you'll write the UTMs. UTMs give you a lot of power. It opens up the full power of the system. You can actually break the system if you're not careful because it allows you to do anything. Even things that you shouldn't be allowed to do, it will allow you to do.
Basically like C.
See, but
Yeah,
yeah.
yeah.
But if you can show us the generic test,
I was
don't know
gonna
towards the
ask
end or
that.
something, because that's, you know, writing C, that's a whole other level of investment, right? But just
Yeah.
the generic one, that
Because I've been
Yeah.
through all the tests and I've never seen the generic one. Maybe I missed it.
You never
but-
seen the generic? Oh,
Yeah.
Oh,
I think
okay.
I saw it earlier when you
It's
had like a
in
device or
here
something.
under devices, I think. It's in here somewhere.
Under devices.
There it is.
Okay.
No, that's Vanderpool. That's not it.
No.
Where is it? Generic device. Here it is. 7-terminal,
Oh, no.
8-terminal.
We need
So
a
you
4-1.
Oh, then,
Yeah,
okay.
so you can load these up.
Okay.
It's just a
And it has
box.
like a bunch of tests under it, right?
No, you have to add the tests. It doesn't have anything.
Nice.
Oh,
I mean,
okay.
maybe at the end, or I don't know when you
Yeah,
want to do
so,
it, but at some point,
so, okay,
would be
so
good to take
If we
a
want to
look.
add one, we can add it right here. We can say generic device add, and it'll throw it in here.
Okay.
And it recognizes that it's a new device, so it creates a new folder for it. And then we can go there. Now we got to add a test. So what do you want? What do you want to test on that generic device?
4-point
Say a
measurement.
4-wire measurement.
Yeah, resistance.
Okay, like Vanderpool. So we can go here. Well,
Yeah, we
let's-
can do Vanderpool, or
okay,
we
so let's
can.
see, Vanderpool.
4-point probing, basically.
Let's see, branch gate out. Search. Oh, can find it. Let's see.
It's slightly easier to use the checkboxes on the right.
Or can we do one that's not built in, like not a built-in Vanderpool, just like set it up ourselves? So because then we can do whatever
Right,
we
with a
want.
UTM, you mean?
No, not UTM, but can you just
A generic ITM.
basically you?
This is a generic ITM.
But we
Okay.
mean
You have
also
to
a
add
generic
the-
test.
Yeah, that's what I'm, yeah,
Oh.
we can do that.
Yeah.
So, yeah, we can go to test, let's clear this. So here's all the tests we can add, right?
It's like generic
So-
IV.
Yeah. Like for instance, here, like an LED sweep. We can say, okay, I want to add an LED sweep.
Or can we do just a generic one, like not LED, not transistor, nothing, just like
An
I want to
IV
set up
sweep.
3 SMUs. I want to supply this voltage here, this measure this current here.
That's it.
You know, I don't want to be constrained, but I also don't want to write C code.
You're not constrained.
Okay.
What you do with the pins is what matters.
Yes.
Oh.
So you're not really constrained.
So
Okay,
it doesn't
I mean-
matter what that
It
says.
doesn't matter what
Yeah,
this
yeah,
says, really.
Okay, I
It
mean,
really doesn't matter.
I mean, let's take a look because
Okay.
I mean, the past when I've used it, it was then often constrained. Like some things you just couldn't do in the transistor one, but maybe that's not the case here. I don't know.
No, it's not. So now, let's like, for instance, I added this LED sweep, and now I can go configure, and see, it's generic,
Okay.
but even though I can change the name of this.
Right,
I
sure,
can call it,
that'll
I can
sound-
call
yeah,
it
yeah.
generic,
Right.
right? But just because
Right.
it's an LED sweep, because it's set up to do a typical LED sweep, but I can
Right.
change it to whatever I want.
Okay.
So now I can say, okay, what do I want to do on this pin? I got all these choices. So
Okay.
the SMU has many modes that it can be used in, right?
Right.
It's a voltage source, it's a power supply, it's a current source, right?
Let's go current source.
It's a list sweep, it's a logarithmic sweep, it's all these different things. So you decide, so you want to do current source?
Current source, yes.
Okay. So we can do, you want to do a current linear sweep, a list sweep, log sweep?
No sweep,
Step?
just source.
So then,
Just a current bias?
Yes,
Okay, so we have
Current
current bias. And then we-
Sweep is better than.
For his device.
for my device it's a bias.
So here,
Actually, you probably wanna
there it
sweep
is. So
Sweep
it
is
kind of
better,
shows
huh?
you, it kind of shows you
Yeah.
on the pin what it's doing. It's
Yeah.
just it's showing you just a DC value because it's a
Mm.
bias source, right?
Right.
So it kind of gives you an idea of what
Okay.
what you've set it to. You see?
Okay.
And then I can go over here and I can say, okay, I want this to do something different. I want it to be, say I want it to be ground.
Yeah,
right?
we
I
need
want
a
it to be
ground
common.
now.
Well, it is. So it's showing you that